All right. So you can probably tell from the lecture title that we're going to start talking about processes and threads, and this is probably the easiest lecture we'll have on this topic. It's going to get very sophisticated very quickly, so we'll just dive in. It shouldn't be too scary. I think that all of it you guys can handle. But like I said, it's going to get very quickly to the point where you have to sit down and think very carefully about how your OS works to make sure that everything works properly. So I saw a little bit of discussion on the Piazza about interrupting other interrupts, and it's that kind of thing that we'll start getting into in a couple of lectures where it's like, okay, I need to understand conceptually what the constraints are in my system so that you can make sure it works correctly. Okay, so we have processes, which is of course short for a sequential process because typically the process is a single logical control flow. We're talking about single-threaded processes because we haven't introduced the notion of threads yet. But anyway, this is the primary way that multitasking is actually offered in these operating systems. So we have the program text, what should be done. We have the CPU state, where are we in the execution of those instructions. We have the current memory state because that's obviously part of the execution state, and various other resources we need to keep track of. Open files, open sockets, blah, blah, blah. So Tannenbaum's OS book actually has a pretty good analogy, which is that the CPU is like a chef, and the program is like a recipe, and all of the various bowls or the stuff that's in the oven and so forth is like the process. So you have the recipe is being executed by the chef, and the chef, a good chef is really good at multitasking actually and can do multiple things concurrently, keep multiple processes or multiple recipes cooking at the same time. The CPU is very similar in how it does this. Okay, so the OS is responsible for managing this, and of course, even with a single processor or a single CPU, we can still execute multiple processes concurrently because it turns out that most processes do some I/O and then some computing, and then some I/O, and then some computing. They have what we call CPU bursts and then I/O bursts. And so if you have processes behaving in this typical way, then you can overlap their logical flows and present the illusion of, well, it's not really an illusion. You're saying that they execute concurrently. It's really more of an illusion that they are executing in parallel, but we'll talk about that next lecture. Okay, so you can represent this as a state diagram, which we have talked about a lot in CS124, so we'll just go over this now because it's a lot more relevant. You have to create processes, and they have a number of places they can originate from. Obviously, when you call fork, which you all had to do in the first project, then you can create a new process that's a clone of yourself. There's another process which is really interesting. It's the very first process that's actually started by the operating system. I say init, but that's not actually what we use very much anymore. Does anybody know what we use now? I don't know if you've heard of systemd. Yeah, do I actually say this here? No, I don't. So, yeah, systemd is the new thing. It's causing a lot of consternation among sysadmins. I personally don't like systemd because it's much more complex, but whatever. They're trying to solve a real problem, and it's just that people don't like change. Anyway, so you have various ways to start processes. And so of the processes that are on the system, some of them are able to use a CPU if they had it. So they're not waiting for some I/O operation that might take a million clocks. They're not waiting for that to complete, so they could actually make progress. But of course, for each CPU, we can only really execute one process at a time. So we have a running state where it's actually on a CPU, and we have a ready state where it could run, but it doesn't have a CPU to run on. So CPUs are limited resources. We typically have many more processes than CPUs. And so we have ready processes which would like a CPU. They could make use of it, but you only have as many processes in a running state as you have CPUs. Okay, now, of course, you don't get the CPU right away, so processes will go into the ready state initially. And it's a collection. We typically call it a ready queue. But that's actually a really bad misnomer because the data structures we use to represent the set of ready processes can be very sophisticated. When we start talking about scheduling and we look at how Linux schedules processes, you'll see that it's got a number of very sophisticated data structures that it uses for managing these ready processes. Okay, now of course the CPU is only allowed to be held for a certain amount of time, so when a timer interrupt goes off, then the OS gets invoked and it will boot that process off the processor, so the time slice expires. And of course it can execute the scheduler to pick another process to get the CPU, so that's how we transition from ready to running. Okay, now when we have long-running tasks, we need to wait. And so in that condition, processes should not receive the CPU because there's no way they could progress anyway, so we move them into a special state called blocked. And they stay there until basically some interrupt triggers to say, hey, now you can move into the ready state again. So instead of holding everybody up, we move the process from running to blocked. Okay, so interrupt goes off. You guys have all experienced that now, how wonderfully exciting it is to see interrupts go off. I tell you, when I ran through my house saying, I got hello to print on my screen, it was magical. Same thing, like keys, I can press keys and stuff happens, and it's just same thing. So interrupt goes off. We can typically move some process or processes into the ready state from the blocked state. And of course, they eventually terminate. They could live for a long time, or they might live for a very short time. It sort of depends on, the purpose of the process and also how well it was written, I suppose. But anyway, there's various things that need to happen when a process terminates. So we need to be able to do our add-exit processing. You may remember that from CS124, that if you exit by returning from main or by calling exit, then there's various exit handlers. You can register exit handlers to run, which is actually really nice if you want your program to shut down cleanly. And so those things are run. If you terminate in a few other ways, then you don't get to run add exit handlers. So you sort of probably shouldn't count on being able to do that, but you could. And of course, processes stay in this terminated state until they get reaped, at least on Unix, so that the reasons for termination can be understood by somebody else. So like I say here, various reasons, voluntary termination by the process itself. So it returns from main, it calls exit, something like that. And typically the way that the entry point works for Unix is it'll just be like exit main. So whatever main does goes into exit, and that's the status code that's returned back to the operating system kernel. So that it's a very straightforward way of doing things. Okay, involuntary termination due to an unrecoverable fault in the process. You generate a seg fault, or you have some other issue that occurs and you get a signal that kills you. Or involuntary termination due to a signal from another process. So I Control-C a process and it sends a sigint, and the default sigint handler is kill the program. Or sigterm, which again the default behavior is to kill the program, but you can handle it and ignore it if you would like. Sigkill, thankfully, cannot be ignored. That's the number for that is 9. So if you ever do a kill minus 9 to a program, which you have to do from time to time, it sends a sigkill to the program. Okay, so that is usually sufficient as far as we need, but Unix beefs this up a little tiny bit by introducing a couple of other states, which again you've probably seen before. If you've ever hit Control-Z, anybody done that to, you don't terminate the process, right? You put it into the background, or really what you're doing is you're suspending it, and then you can put it into the background if you'd like. But anyway, that sends a sig stop or a sig t stop to the process, which moves it into this ready suspended state. Okay. Now it may be ready, or it may actually be blocked on some I/O, and so in that case we also need a blocked suspended state to keep track of the distinction there. Okay. So I happen to hit Control-Z, and the program happened to be in the middle of an I/O that's still going to be running for a few 100,000 clocks more. Then it's going to be in blocked. So then it moves to block suspended, and when that interrupt triggers saying, hey, your data showed up, then it can go ahead and move over to ready suspended. Okay, so this is the final process lifecycle, at least as far as Unix is concerned. Okay. I imagine there's probably a way to take a Windows program and put it into the background, but I don't know it offhand. So it probably has something analogous, but I don't know what it is. Is there anybody here who really loves programming on Windows, like Windows system programming? I hear snickers, I understand. But I mean, there's always a couple, and they don't like to admit it, but it's, it's great if you want to do graphics programming. DirectX is really cool. Okay, so how are processes resources managed and reclaimed? How are block processes managed by the OS? How do we switch what process is currently running? So we're going to talk about this probably in more detail than we ever have, but it's still not going to be nearly enough detail to understand what goes on in the OS. So we're going to revisit that question when we start developing the implementation details of how this whole model works. And of course, how does the OS choose what process should run next? So that's really the question of process scheduling. Okay? So these are important questions that we need to understand, and we're going to start going through these basically in sequence as we go ahead and unravel how this all works. Okay, so we have some data structure that represents all of the details of a process. Like I said, the program text is part of this, and also the execution state. So we have things like registers, open files, memory, virtual memory configuration, so forth. Okay, and typically, at least historically, it was called a process control block. In Linux, it's actually called a task struct, and Linux doesn't make a lot of distinction between processes and threads. In fact, threads are kind of what Linux manages and schedules on, which makes it very easy for Linux to support multi-threaded programs. So task struct tends to be how Linux refers to these things. But this is a very simple representative example from older OSs, which I kind of continue to use because it does capture all of the relevant details. So we have identification, state information, status information, so that was, am I able to run if I got a CPU? Am I blocked on some device? If so, what device? And so forth. And hierarchy information and other information. And when you look in Pintos, because Pintos has this thing called a kernel thread, which we'll talk about more starting next time, then it has various details like this in the thread object. So we have, what queue are we in? Are we in the ready queue? Are we blocked on something, and so forth? And then we have some, I can't remember if it actually has hierarchy information or not, but you have all of these same kinds of details in Pintos's representation of processes. Okay, so process identification. We need some kind of process ID. We need to map it to the data structure for the process. Very simple to do. We just need some simple data structure that can map that int to a pointer. That's rocket science. You might think, well, a really easy way to do this is to have an array, and the process ID is just an index into that array, and then the entry in the array is a pointer to the process control block. Well, that would certainly be an option, except you're expecting that you're always going to have most of your processes, available processes to run are actually in a running state, which is kind of a bad assumption if you want a responsive computer. So they tend to use a sparse representation instead. Hash tables are great because it turns out that you can hash ints really easily. And pointers are easy to pack into buckets, so why don't we just use some kind of hash table representation? Okay. Now it kind of introduces a new question, which is, if you've got this hash table and it's living in the kernel, and the kernel has a limited amount of memory, then how do we actually do kernel memory management? That's something that we're going to talk about in the future. But you might remember how we talk about memory fragmentation issues in CS124. And remember that fragmentation is an issue the longer that a program runs, and especially if the program allocates blocks of varying sizes and then releases them. They have various life cycles, and they're allocated and released. Well, there's one program that runs longer than any other program on your computer. It's your kernel. And your kernel frequently has a lot of different size things that it has to allocate. So how we manage memory in these systems is important, and it also has a lot of subtleties. So we're going to revisit that issue in probably a week or two and talk about how kernels actually manage memory, because it actually affects how these APIs are exposed, and it affects how kernels frequently work with user programs. So we'll revisit that in the future. Okay, now we also have process hierarchy, where you can see we have a parent process and a list of children. Every process has to have a parent. Now, this is a Unix constraint. This is not a Windows constraint. Windows has a very much looser way of doing this. But every process has a parent, except, I suppose, init. Init doesn't have a parent because, it's the very first process, or the equivalent in System D. And if a parent process terminates before its children do, then the children become children of init, or the whatever the ancestor process is. Anybody remember what it is for Macs? The equivalent of init on the Mac? I can't remember off the top of my head. It's launchd. That's what it is. Launchd is the parent of every process on the Mac. So you can see that different operating systems have different solutions for this. It's not always just necessarily init. Okay, so yeah, not every operating system provides a hierarchy. Windows is a notable example that doesn't really impose a hierarchy. You can group processes and you can have leaders of groups and so forth, but they all are kind of peers on Windows. Okay, state vectors, so this is all the context information. So you have CPU state, what process capabilities do you have. I was working on an interesting project, and if you want to set resource limits on processes, your process has to have certain privileges to do so that are obviously associated with being the root user or some user in a particular group or things like that. So you have capabilities, protection information. When it's suspended, you have register state, you have program counter, you have other details like that, flags, and let's see, CPU number when you're running. So this is interesting. If you have multiple cores, it's nice to know which processor you're running on, because maybe when you resume that process, you'd like to resume it on the same processor, just in case there's still memory in the cache that process will now not have to load from main memory. So there's things like that. Also, sometimes you've probably heard of specifying processor affinities. So you can actually say, I would like to always be on this one processor when I run. And again, typically that's done to maximize cache utilization of programs. Memory, so contents of the process code, data, stack segments, and so forth. And then various other resources. Network sockets, files, pipes, Unix sockets, all of those kinds of things you might have listed in your resources. The things that the process has open. Because guess what? When the program terminates, all those resources need to be cleaned up by the operating system. You remember the whole thing of process A opens a file, process B deletes the same file, now there's no more directory entries to the file, process A terminates, now the OS needs to go in and actually clean up the file that process A had opened. So those kinds of things need to happen, so that's why we have a collection of resources. Now there's also scheduling details, so we have these kinds of states, which we already talked about, basically saying, what is the current status of the program? Can it actually run if I gave it a CPU? Is it blocked on some device? And of course, there's various other details as well that we might want to record, like what's its behavior, so that we can do scheduling and so forth. Okay, so those are basically, let me go back here real quick. So those are basically all the general details that we capture for every process. We can add other details. We'll actually start developing this model a little bit more to make some of our operations pretty easy. But are there any questions about the process information that goes along each process? Okay, this is like pretty easy so far. So we haven't gotten into anything really, insanely complicated. Okay, so process A is executing along, and then something happens. Maybe the disk controller fires an interrupt to say that some sectors got loaded into a disk buffer that the OS set up. Or a timer goes off to say process A should no longer have the processor. Or let's say process A decides to open a file or something like that, and we know that it's going to take some time before that thing can actually be open. Okay? So when that event occurs, we switch into the kernel. And we've only talked very briefly about this. We understand that there's kernel space and user space, and we have some protection capabilities. We understand that the code is probably running in this user mode thing we've talked about, and now we need to switch into kernel mode. But remember that all of this goes through an interrupt handler. So you all have written interrupt handlers now. If you haven't, then you're way behind on the second project. But what's one of the very first things you do in the interrupt handler? Anybody remember? Yeah, you do like a push A, right? And that pushes all the registers onto the stack. And then you can, I can't remember, does that push the flags register, or do you then have to do a push F? I can't remember.
I think flags are automatically.
You're right, because the interrupt flag is cleared, and then, so, yeah, the original flags is saved before, as part of the interrupt dispatch process. Okay, so you have all this stuff that's pushed onto the stack. Well, guess what? If I hand somebody a pointer to that data on the stack, that can be the program's context. At least now I have the register state saved. I can save a few other things if I'd like, and that actually can be exposed. There's some Unix APIs for signal handling that expose that information. It's crazy. Because if you manipulate that, then on the trip out of the interrupt handler, all of that gets restored, and if you made any changes, the changes get applied to the registers as well. But so we have some basically details of the process's execution context that get saved when we do the trap. Okay, so this is the kind of thing that's going on. CPU state, registers, program counter, stack pointer, status flags, all of these things are saved by the interrupt dispatch process. And then various other things are already saved into the process control block. There's another good reason why we have to do that, because the kernel needs to run code, and the kernel doesn't want to have to worry about blowing away the process's details. So all of that information needs to be saved so that the kernel can then do its thing. Okay, so we have a little bit of time spent on saving CPU state. We do kernel task stuff. Then we have to, let's say that we switch processes. Okay, and so in this case, let's say that it's something other than get PID or get ppid, which are very simple operations to perform. So they're opening a file, the timer interrupt went off, and they have to get kicked off the CPU, something like that. So the kernel ran the scheduler. It said, okay, now it's process B's turn. And so it switches to something else and then exits out of the interrupt handler. And that restores the CPU state of process B. And then process B gets to execute. Okay? So this is a rough guide as to what's going on. And you can think of like what is going on in each of these details. You'll see it much more when we get into the implementation of this stuff. The important detail here is that this definitely takes time. And while we're spending time doing this stuff, we're not spending time running actual real program code that we care about. Okay? So, like I say here, the entering into the kernel, we probably will have to switch stacks. So you use your task segment configuration, all of that kind of stuff. Yeah, and like I have here, you save the program counter, you save the flags. Probably the very first thing in your interrupt handler is you're going to save all the registers so that you can do whatever you want in your interrupt handler, blah, blah, blah. Okay, then the kernel has to run the scheduler. You want the scheduler, remember, it needs to be fast and it needs to make good choices. Good luck with that. So that's an interesting challenge. Most system calls will cause a context switch, so most system calls will invoke the scheduler. Okay. Then on leaving the kernel, you have to restore the CPU state, and we kind of made that sound easy. Okay, we have a push A, and then we just pop A, and that restores the CPU state. Well, it's a little bit more than that, because we also have the virtual memory configuration, and we have to load the virtual memory configuration. So that's another thing that has to happen. So control register CR3. I don't think you specifically have to mess with this. Thankfully, I don't think you have to ever mess with this directly, because Pintos has little helper functions to do these kinds of things. Okay, so I have to switch virtual memory from one page table to another page table. Thankfully, the kernel is mapped at the same location in both page tables, so it won't map itself out of existence, which would be another fun gotcha if you had to write that part yourself. If I change out the page table, what else do I have to do? Is the page table the only place that page table entries are stored? I'm getting grumpy because you all should know the answer. We talked about this in CS124. Man. Oh man. Translation. Look at side buffers. Yeah, right? So that's the other place where page table entries are stored. If I change the page table, are those entries valid anymore? Not really. So I need to flush the translation look-aside buffer cache, which means I'm going to have slow memory accesses for a little bit while it gets reloaded. So that's another thing that has to happen here. Okay, so you can see that all of this slows things down. We would like to avoid context switches if at all possible. That's why a rough estimate of the impact of a context switch is about 20,000 instructions. That's the kernel tasks part. That's the part of saving the PCB state, restoring PCB state, flushing the translation look-aside buffers, and off you go. So it's not free. It definitely costs a little bit of time and energy and effort. Okay, so we want to minimize the amount of time this takes. And when I say 20,000 instructions, I should probably also say that's on IA32, x86, 64, because it turns out that there's processors with hundreds and hundreds of registers. And they'll actually group them into register files. And if you want to switch processes, all you really do is switch from one register file to another one. That's a lot faster. You know, so it just depends on the technology that you're using. Sometimes context switches can go a lot faster, but still, they're going to take some time. They're not free, and while you're doing them, you're losing time to do other things. Okay, so that's important. We also have these queues, and we're going to start talking about how we actually manage processes that are blocked. Typically, we will have some kind of queue, and you'll notice that it's a very different approach. I want to actually spend some time in a future lecture talking about how to think like a systems programmer. Because there's a whole bunch of stuff you do in user space that if you tried to do in a kernel, you'd have the worst operating system implementation ever. And so I'd like to spend a little bit of time talking about that at some point in the future. But you get a hint of it here, and you'll get a hint of it when you get into Pintos, where you have one data structure, and instead of having linked lists where elements point to that process control block, the process control block itself holds the pointers to previous and next elements in the queue. And you can actually run multiple linked lists through a single data structure. And so it's a very clever optimization of memory management and so forth so that you don't have too much to actually manage as far as dynamically allocated memory. So we have queues. Elements hold pointers to the relevant process control blocks. You can think of it that way conceptually. And so you have a run queue or a ready queue that holds all the processes that could run would they have a CPU. It may be that we do things way more complicated than just having a simple linked list. Remember multi-level feedback queues? Well, we might have 16 queues instead of just one. Okay, and somewhere you have an array that points to the first element of each of these queues. You have something like that. Linux happens to manage like a binary tree for some of its schedulers. I can't remember if that was the completely fair scheduler or the O1 scheduler. We'll talk about those when we get to them. But basically it keeps all the processes in a tree in sorted order by priority, and like the bottom left one is always the one that gets to execute next. Okay, so it can be much more sophisticated than just a queue. But we still call it a ready queue because we're simple like that. Now, since processes do block on long-running operations, you see we can block on peripheral read, things like that, read data from a network socket, wait for another process to terminate. You call wait PID, things like that. You call sleep, which is really nice. You have various things like that. You need to get them out of the ready queue and store them somewhere until they can proceed again. And typically it's an interrupt handler that says that process can now progress. Now, interrupt handlers have real serious constraints on them. You guys may have run into a few of those kinds of details on your second project, but you're going to run into a whole bunch more when you start getting into Pintos. One thing interrupt handlers are never allowed to do, I don't know if anybody knows this offhand, but one thing interrupt handlers are never allowed to do is to block until something can, until they can proceed. Interrupt handlers are not allowed to do that because guess what? They interrupt everything. They hold the CPU. They're not allowed to block. They have to run to completion. And so like I say, it has to be short, simple, and fast to keep from holding anything else up. So to solve this problem, to make it easier, OSs don't just keep one collection of block processes, because if they did, then the interrupt handler would have to be like, oh, I'm a timer interrupt. Let me run through all the block processes and see which ones are waiting on a timer. Okay, these are, and this subset is now able to proceed. So I'll go ahead and move that subset into the ready queue. Why mess with that? Why hunt through a whole bunch of processes that it doesn't care about? So what the OS will typically do is maintain a queue for each device that things can block on. And that way, when the interrupt handler goes off, it knows exactly which queue to look at. Okay? Now, there's many other things that you can do in here as well. I'll just give you like a big, ginormous hint for the third project. One of the things you have to do is implement passive sleeping. I don't care if you do polling or spinning on something in Project 2, but you're not allowed to do it in Project 3. Project 3 is where you have to start becoming sophisticated. And so what you can do is maintain a queue of processes that are waiting on the timer. And there's various ways that you can do it, but one easy thing to do is to always store them in order that they need to wake up. So that the ones that need to wake up soonest are at the front, and the ones that need to wake up furthest in the future are at the back. That way the interrupt handler will always run as short as possible, because it can just go down that queue until it's too far in the future, and then it can stop looking down the queue. So there's things like that you can always do to make your interrupt handlers a little bit faster. And that'll improve overall system responsiveness. Okay? Things like waiting for a signal. Well, you can create queues for various signals. You can create queues for processes. I mean, there's a lot of different ways you could structure this. One thing you have to do is think about, well, how many processes generally are actually going to be waiting in this context? So you have to think about how you actually want to structure these kinds of things. Thankfully, this is not something you have to care about very much for Pintos. But if you're designing a real operating system with things like child process termination, that you need to reap the child and so forth, then you have to think about these kinds of design questions. Do I want to have a queue per process? Do I want to have something where I can chain processes to another process when they wait so that I can inform them right away? You have to answer those kinds of questions. Are there any questions so far? All right, you can probably see exactly where this is going. This is not terribly complicated yet. So this is an example of how we might structure our system. Okay, we have our ready queue, which again may not be a queue, but it's definitely processes that are ready. So they're waiting to receive the CPU. The line going to the right of the ready queue is obviously governed by some scheduling mechanism. We'll talk about where scheduling fits into this picture in a second. But new processes come into the ready queue. Processes that are booted off the CPU go back into the ready queue. And processes that become unblocked go into the ready queue. Okay? If it terminates, it goes off the CPU into nowhere. So it goes ahead and terminates. If it decides to perform some long-running task, then based on the device that it has to wait on, or based on the circumstance, it goes into a corresponding wait queue to say, this is now what I need to wait on. So you access the first physical storage device. Well, that thing can generate interrupts. And so the dev HDA queue would be traversed by the dev HDA interrupt handler that goes ahead and figures out which processes can then proceed after a read or a write completes. And then it can go ahead and move back into the ready queue. Okay? So again, this is one of those things, when you look at Pintos and when you look at real operating system implementations, you'll often see that these task structs or thread structs will have one queue pointer, or one set of queue pointers that basically correspond to which queue the thing is currently living in. And so you can see how a process would move from queue to queue as it does various things. So you really only need one. You don't need one for each. That takes up too much space. Okay, any questions? Alrighty, so what's really neat about this is you'll get to build like very simple little versions of this in Pintos. So it's not like you have to implement the whole kit and caboodle yet. You can just start out with very basic stuff. Like you'll build a timer queue, and then your scheduler will start getting a little bit more sophisticated on the ready queue side of things. So you'll see how it all fits together as you get into Project 3. Okay, yeah, it is a large and complex topic. It's really cool. I can't wait to talk about it because there's stuff in there that blew my mind when I saw it, and it'll probably blow your mind as well. So I'm kind of really excited to get into that topic, but not right now. We'll talk about it in probably a week or so. Scheduling can definitely be applied at different levels, and this is another thing you may not be familiar with. But when we think about scheduling, we typically think of who gets a CPU next, but there's various other places that we can apply scheduling as well, and that historically were applied very heavily. So you have long-term scheduling or job scheduling, which is basically who gets to start running. So this is, I'm queued up on the tape, waiting to run. When do I actually get to become a new process that starts to execute? You may have heard this term spooling before. Typically you hear it in the context of printing. But in these batch execution systems, it was the job is ready to execute. We need to go ahead and load it into the system to execute. And spool actually is an acronym, which I'm not even going to bother to try to remember. You probably shouldn't either. But if you're curious where that term came from, that's where it came from. So basically the long-term scheduler has to pick who gets to start running. And if you think about it, we don't have anything like this on our current computers, which is fine. We don't really use them that way. But if you had 20 jobs and you can only run 5 at a time, which 5 do you choose? What might be good things to think about when you're trying to figure out which 5 of 20 jobs should actually execute? Anybody have any guesses? How long the job is going to take. If we know that, that's a great thing to know, how long the job is going to take. Any other ideas? Yeah. Oh, you just putting your hand up. So, yeah, do you have an idea?
So if like we have one job that does a lot of I/O, I would want to start that job first.
Okay, so that's an interesting one. If you have a job that does a lot of I/O, then you might want to start it before some job that does a lot of CPU. That's another interesting one. If you know that, which is always interesting because part of this is like guessing how jobs are going to behave. Let me go ahead and start spelling this out because we don't have a lot of time. Basically, the goal of the long-term scheduler is to try to maximize the utilization of all of the hardware in the batch processing system. You guys are starting to think about these things as you talk about this. What if all the processes are I/O bound? What if we only had I/O bound processes to run? How much would our CPU get utilized? Yeah, like hardly. Oh, it would make me sad. Basically, it'd be handling interrupts all the time. That's all it would be doing. And then we go back to waiting on stupid tapes. Okay, so that's bad. We wouldn't get to use our CPU much. What if all the processes were CPU bound? Well, there's a couple answers to this one.
Either some processes don't get to run fast enough, or some processes just take forever.
Basically, yeah, they're all competing for this one shared resource. Context switches become the bane of our existence because anytime we spend context switching, we're not using executing programs. So we basically would get into a situation where it's like, well, just let one go and let it finish, and then let another go and let it finish. But the thing is that we're definitely not utilizing our peripherals. So we have a couple of issues that we can run into with CPU-bound processes. So what the long-term scheduler tries to do is get a good mix of I/O-bound processes and CPU-bound processes. Because while the I/O-bound processes are waiting for I/O, that processor can be used to do CPU-bound process stuff. And then when I/O becomes available, then the operating system can kick off the CPU-bound process, let the I/O-bound process do its thing a little bit, and then keep the I/O peripherals utilized. So basically, the long-term scheduler is trying to maximize the overall utilization of all aspects of the hardware. You can probably imagine why this was important for batch processing systems because I'm paying a lot of money for this big, giant, room-sized CPU and my printer, and I don't have a monitor. I just print everything because I suck, and that kind of stuff. Okay, so long-term schedulers would run on the order of every few minutes. I think you can get to that. So anyway, a process terminates. I need to figure out who comes into the system next. That's when the long-term scheduler would make some decisions. Okay, now we typically don't have a long-term scheduler, or should I say it this way, the user is the long-term scheduler, because if the OS becomes unresponsive, or I get grumpy because my disk is churning all the time and I'm not actually able to get things done, then I'll just kill things myself. So I'm the long-term scheduler. You're the long-term scheduler on your system. So we really don't have that anymore. We basically only have short-term schedulers, which govern only the CPU. Okay, so that's the short-term scheduler. There's another one which is interesting, which let's say that the long-term scheduler makes bad choices. Well, in that case, the medium-term scheduler can actually suspend and resume processes on its own. So if you're wondering why we have suspended processes, like on Unix, it's not just so that people can hit Control-Z and then go do something else. It's nice, but that's not a good enough reason to take the time to implement all that stuff. It's because medium-term schedulers needed a mechanism to actually be able to tune the process mix when they actually, the long-term scheduler made bad choices. If you suspend a process and it's not receiving the CPU anymore, what can we do with its memory? Page it all out to disk. So now we've freed up all that physical memory for other processes to use. So you can imagine that a medium-term scheduler has a lot of power to free up resources when you have too many processes using the wrong kinds of resources for everybody to get along well. So that was the purpose of medium-term schedulers. Again, we really don't have medium-term schedulers. I think maybe, okay, so I graduated in 1998, and so UGCS was still a thing in 94. We could all sit and work and stuff. And I think over that 94 to, so 22 years now, I've probably suspended processes so that other things can run maybe 3 or 4 times. So you can imagine, okay, medium-term schedulers, probably a great idea when they were needed, but they're not really a thing anymore. Okay, but this is where these schedulers slot into this picture. And you can see that I've really simplified things, okay, because the block suspended queue and the block queue are going to be much more sophisticated than we actually have in the picture. And the ready queue we know is going to be more sophisticated than we have in the picture. But this is where the schedulers govern things. So the long-term scheduler governs entry of processes into the ready queue, so when they start. The short-term scheduler governs who gets to move from ready into the CPU. And the medium-term scheduler governs who goes from ready back to ready or simply back to a suspended queue instead. Okay, so the medium-term scheduler gets to govern those kinds of things. Any questions? This is your 1,000-foot view of process management and process scheduling. So if you have any questions now, it's good. If not, then what we'll do next time, so I think this is the last slide, is start talking about how we build threads into all of this and how we implement this on the system. So we'll start talking about that next time. So today we're going to start diving into threads. So we already talked about processes, and this is not something new because we all saw that kind of stuff in CS124, and then you got some experience with it, even more experience, I should say, in the command shell project. So you get you have a pretty good sense of that. But now we're going to start talking about threads as pertains to how you implement an operating system that has threads. So processes previously only had one thread of execution, which means you only have sort of one instruction that you're executing at a particular time. But it is becoming really common to have operating systems with threading support. So now I can have a process with multiple concurrent threads of execution, all going at the same time. Or we put at the same time in air quotes a lot of times because it actually is not exactly at the same time except in specific circumstances. So anyway, but we are starting introducing this notion of concurrency. We do need to change our process model because now that we have multiple threads of execution, not everything can be maintained at the process level. And there's certain things that should be pretty obvious. CPU state. Do I need to be able to have a set of registers for each thread? Well, yeah, that would be really important because each thread may be doing its own thing with the registers, so now we have to have some way of storing registers per thread. What about a stack? Okay, yes, a stack is also another thing that needs to be stored on a per thread basis. So there's certain things. These were the items we had before per process, so address space or page table, some kind of page directory, the program itself, CPU registers, program counter, stack, blah, blah, blah. You can go down the list. And when we move to multi-threaded processes, there's some things we keep on a per process basis, so you can still have one program for the entire process. The various threads share one program. The various threads share the same console and a few other details like that. But then you also have a few details that you factor out for each thread. So CPU registers, program counter, and stack pointer. Those are the things that we have to factor out if we're going to support multiple threads of execution in a given process. Okay? Any questions so far? It's going to get rapidly much more complex than this. Mainly next time. So come Monday, because it'll get pretty detailed on Monday. But there's a couple of reasons why we'd like to have multi-threading. There's a really obvious one and a much less obvious one, unless you've actually tried doing other ways of concurrent programming, and then it's also really obvious. But what's a really obvious reason why we might want to have multi-threaded processes? Anybody here written multi-threaded programs, I hope? Yeah? So, why?
Speed it up.
Speed it up. That's a really obvious reason. And if you look at even just the performance side of things, there's a variety of sub-reasons why we might want to have multiple threads in a program. The second reason, which is much less obvious, is that threading provides a cleaner abstraction than the alternatives, which are grungy and bug-prone, which we will be talking about. When we get to that point, I want to actually talk to you all a little bit more about this to see if you've had experiences with these things as well. Okay, so there's lots of ways that multi-threading can improve performance. One is responsiveness. This is one that we all experience every single day that we use computers, whether you realize it or not, because almost always we have long-running operations, like downloading the image that goes in this web page, that we'd like to not have to wait till it's finished. And so what we can do is have multiple threads, one that's responsible for doing the slow thing, and then another one that's responsible for responding to the user. So we have a foreground thread for that. We have long-running tasks in other threads that don't hold up the responsive thread, and the user is happy because they do things and the program responds right away. And web browsers are probably the single most common example of this because they have a pretty complex task of rendering a web page. And anytime you visit a web page, you may be downloading anywhere from 12 to 24 different files. And now we have scripts and CSS files. These things didn't really exist when I was first using the web because I started in 1994 and it had just been published in 1993. So we didn't have all those files. We have even more now. And so we have to have ways of managing, accessing all those things, and still providing a responsive program. So yeah, user interface thread draws the page, handles mouse clicks, background threads suck stuff off the internet, and then the user interface thread updates as the files become available. So that's generally how these things work. Okay, so given this, here's a question. Does this approach require multiple CPUs to actually get a benefit? I have one foreground thread doing user interfacey stuff, and then I have background threads sucking data off the internet. Does that require multiple CPUs? I'm not seeing any heads nodding. I'm seeing a lot of shaking. Why not? Think about the state of those threads. Yeah, do you?
You can make some of them nicer than others, and some of them be run more often.
You could make some nicer than others, but do you need to even? What are those threads going to be doing most of the time? Yeah, they're mostly going to be blocked on I/O. So, that's really cool. Computers and operating systems love threads that are blocked on I/O because guess what they have to do? Nothing. They can just sit there and wait till some interrupt fires, and then I move them out of that queue into the ready queue. So this is really nice. The user interface thread will also almost always be waiting because users are probably the single slowest thing that a computer can interact with. And you think the internet is slow, just wait till you wait on a user. So even with a single physical processor, you get huge benefits, performance benefits, by using multiple threads of execution. And again, this is about responsiveness. We're not really making the entire system go faster, although technically I think you are if you have multiple concurrent operations that you can then parallelize, because they, data from different servers or even data from the same server may come in at different rates for different requests. And by overlapping those things, then we can get a huge performance benefit. But this is really more about responsiveness. Now here's another one. We have a scientific or mathematical computation. I have a friend who, when he was in graduate school, was doing molecular dynamics simulations, and he was doing them on a single processor, and he said, I want to make this faster, so he asked his boss for an 8-core system, and he got it, and so he started figuring out how to write a parallel version of his program, and I helped him with a huge chunk of it. We both learned a lot from that experience. But like it says here, instead of performing the computation in a single thread, split it into multiple concurrently executing threads. So again, does this require multiple CPUs to yield a benefit? And if so, why? There's a really easy answer. This is not a complicated question. Why does this require multiple CPUs to yield a benefit? Yeah. They're all doing the same thing, but there's a specific thing that they're all doing, which is using the CPU, right? So if we need to, factor this thing into multiple pieces that are all using the CPU, then clearly we need multiple CPUs to see any benefit. Now, what would happen if we tried to do this on a single processor? Would it run the same speed, or faster, or slower?
Slightly slower.
Why slightly slower?
Context switches.
Yeah, we have additional overhead that we're now introducing. Context switches is one. You probably will have synchronization overhead, because almost all computations need some kind of aggregation phase where you combine intermediate results into something that every thread can share. So we get various overheads that start to be introduced. Okay, so this is one of those things that experience with systems programming really helps you to understand the reasons why. I've got an I/O intensive task. Well, probably threads could make it better. If I have a CPU intensive task, then probably threads will only make it better if I have CPUs as well. Okay? Just to give you another example, because I run into this one very frequently, in the CS11 Java track, we have the web crawler, and then we have the multi-threaded web crawler. And even now, it's been 10 years since I've been teaching that track, and you have this web crawler, and you run it on 50 threads, and you see this huge performance improvement, even better than 20 threads and 10 threads and so forth, even if I only have one processor. That's how much we'd like to overlap internet interactions when we write programs that interact with the web. So in those situations, even though you only have one processor, having 50 threads gives you a huge performance benefit. If I was doing a really compute-intensive task, 50 threads would make it much worse if I only have one processor. So it's one of those things. Understanding why that is kind of really important in systems programming. Okay, so here's another. This is sort of a corollary, and it's probably, again, obvious to all of us. So a single-threaded process cannot take advantage of multiple CPUs. If I have multiple CPUs, the only way I can take advantage of it is if I have multiple processes or I have multiple threads running in a single process. There's caveats there too, which we'll start talking about toward the end of the lecture. So you can see that we get scalability benefits from multi-threading. That's another aspect of performance. We already had responsiveness. Scalability is another aspect of this multi-threading that we like to leverage. Okay, now another thing to keep in mind is that we have concurrency and we have parallelism. When we have an I/O-intensive task that we run in multiple threads on a single processor, what we're doing is we're increasing concurrency, but we still have the same amount of parallelism, which is not much. Okay? Concurrency means that you have tasks, different tasks that you're performing at the same time. So their logical control flows overlap. That's all that concurrency is. So you can have concurrency on a single processor system. So yeah, that's what I was just saying. So one CPU system can achieve this by switching back and forth between tasks at appropriate points, ideally when they block, things like that. But concurrency doesn't automatically mean parallelism, because parallelism means I have two things happening at exactly the same time, i.e. I'm running two different instructions at the same time on two different processors, which have a shared memory region that I need to coordinate access to or something like that. So you can see that parallelism introduces fun and new, exciting bugs to solve over concurrency. And typically when you're working on system software that is concurrent and has the ability to be parallel as well, it's a good idea to work on it on a multi-core computer so that you can actually see the bugs due to parallelism as well as the bugs due to concurrency, because they are slightly different. So there's interesting challenges and subtle differences between them. Okay, so that's something important to keep in mind. Okay, so we had our scientific mathematical computation, and we're splitting it into multiple concurrent threads. We'd expect that if we have multiple CPUs, and let's say that we choose the same number of threads as CPUs, or let's say that the number of CPUs is an upper bound on the number of threads we create for our program, these threads will execute in parallel. So they're compute intensive, each one has its own computey thingy, so they can run in parallel and we should see a benefit. Ideally, if we run our program, let's say here it says 1 unit of time to complete on one CPU, and we run it on n CPUs, we should see a speed up of n, or it should take basically 1 over n amount of time that it would have before. Okay, so 1 unit of time on one CPU, 1 over n amount of time on n CPUs. Is this what we see in real life? Only in our dreams, really, unfortunately. This is sort of la-la land. The reason why is because almost always we have some amount of our program that has to execute sequentially. And that sequential part basically constrains the rest of the program to be able to run in an efficient way. Let's say that like 10% of our program was sequential and 90% of it could be run in parallel. What's the fastest we could get that? If we threw like 10,000 processors at it, how much faster would we get it to be? Yeah, 10x is a limit there because 10% of our program is sequential. What if it's 5% of our program that's sequential? What improvement? What's the best improvement we can get there? It's easy, right? Because I just gave you the, 10%. Now 5% would be 20x is the best you get. You run it on 1 billion processors, you're still only going to see a 20 times performance improve. That's really disappointing. It's kind of in the same way. It's exactly the same as caching performance. If I have like a 95% hit rate on my cache, then my program is still going to run pretty slow if main memory is really far away from the processor. Similarly, if I have a big chunk of my program that's must execute in sequence, and the rest of it can be parallelized, then I have a program that I cannot really improve its performance by running it on many, many processors. Okay? This is actually captured by this mathematical expression called Amdahl's law. Who's heard of Amdahl's law? Okay, a few of you have. I don't know if you heard about it from me. Hopefully not, because it's actually really important nowadays. So you have a task where S is the percentage of the task that can be executed serially. Or like I said, it must be executed serially because it cannot be parallelized. That often happens when people try to parallelize a program. They parallelize it instead. So a single processor machine, the task takes 1 unit of time to run. On an n processor machine, you get this improvement. So you have S, which is the serial part. That's really obvious. Then you have 1 minus S is the parallelizable part over n. That's how much time it'll run. Really obvious expression, right? Well, somebody got their name attached to it. So, come up with simple expressions and you might get your name out there somehow. Okay, so the speed up due to parallelism is just that, 1 over that. Okay? So S plus 1 minus S over n, and then the speed up is 1 over that. So we already talked about a task with 10% that must be run serially. If you put it on 2 CPUs, you get a 1.8x speed up, 3.1x for 4 CPUs. You're already starting to get really sad because you're thinking, wow, all that effort to parallelize my program wasn't very good. 4.7 times speed up on 8 CPUs, and of course the fastest you can get it is 10x. And this was kind of the experience that I had with my friend and his molecular dynamics program, because every computation had a big chunk of it that could be parallelized, but then there was a little part of it that had to be sequential, and we saw similar results to this. I'm adding more cores, and it's not going up by n like I wish it would, or being reduced by, divided by n. The execution time's not being divided by n. That's really making me sad. Okay, so people saw Amdahl's law. I can't remember exactly when it was devised. I think it was in the late 70s or the early 80s or something like that. So people saw Amdahl's law and they said, why do we even waste time and energy on parallelizing computation? Big giant server farms are dumb. Well, what do we do nowadays? We have big giant server farms. Why is that? It turns out that Amdahl's law is a very specific expression for a very specific circumstance, and that's when we have fixed size tasks. Almost always, that is not at all what we want to do. You think about, let's see, given more computing resources, I want to increase the size of the task. I'm simulating rocket engine fluid flow because I want to see if my rocket's going to go where I want it to or explode. Which is it? And so if I have 10 computers, I might put my data points in my simulation so-and-so close together. But if I have 100 computers, maybe I want to have a much finer mesh for my simulation, my fluid flow simulation. I want to do my climate modeling computation. And if I have this many computers, I'll simulate it at this level of granularity. But if I have 10 times the computers, then I'm going to greatly increase the number of data points in my climate simulation. So you can see that when we have more computing resources, we don't hold the problem size fixed. So anybody that says Amdahl's law is the last word on parallel computation, well, in one sense it is, but in another sense it's completely irrelevant because when we have more computing resources, we always increase the complexity of our computations. Same thing with like server farms for rendering movies and stuff. Well, what happens if my server farm gets larger? Well, I increase the quality of my rendering or I increase the resolution or both. So it's like, I make use of that. And so what you notice is that there's a certain characteristic we can take advantage of. As the task size increases, you have the parallelizable part and it grows at a certain rate, and the serial part grows at a certain rate. So if the parallelizable part grows faster than the serial part does, then the percentage that's serial actually is going down. And so we get a big benefit as we scale up our problem and scale up our hardware. So this is why we do like server farms, and this is why we like to throw large computations at large clusters of computers, because we do see an improvement. We increase the problem size, and we get an increased benefit from parallelizing it by doing so. Okay, and like I say here, this has been formalized as Gustafsson-Barsis law. That was late 80s, so this is why I vaguely recall that Amdahl's law was in the early 80s. And people, like I said, got a little bit depressed until they thought about it a little bit more carefully, and they realized, oh, actually, there's a really good reason to keep scaling up our computing resources, not just physics. Okay, any questions? So this is a pretty important detail here. I just wanted to mention this. Okay, few other benefits, like I say, are resource sharing and economy. So when I have a multi-threaded program for managing resources, then I actually have a benefit over running multiple processes that can't share resources very easily. Threads tend to be much faster to create and destroy. They have fewer resources to allocate and release, so that's nice. Also, context switching between threads in the same process is actually faster because there's certain things I don't have to do. Remember, they share address space. And so if I switch from one thread in a process to another thread in the same process, I don't have to change the MMU's configuration. And if I don't change the MMU's configuration, then I don't have to flush the translation look-aside buffers. And then I get to keep using the fastest cache on the computer. So that's nice. That's a big benefit. Sharing resources between threads is much easier than sharing them between processes. Having done both, I could definitely attest to that. You just say, here's a pointer, and the pointer means something because you're in the same address space. Processes can't really share pointers very easily. You can open shared memory regions at the same address ranges in two processes. And then you can share pointers as long as you make sure the pointers are only within the shared memory region, but you have to be very careful. So here's the other one, and we're going to spend a little bit of time talking about this, but I asserted that you get a big benefit in the abstraction side of the picture from multi-threading. And we'll explore this a little bit now. An obvious question, you may not have thought of it quite yet, but there's a pretty obvious question when you think about it, which is why are all our long-running calls blocking? You could imagine that you could create long-running calls that are not blocking. You just say, hey, I want to do this thing, and the computer says, no, it's not done yet. Then you say, well, I want to do it now, and it's like, no, it's not done yet. So it comes back right away instead of just blocking and making the process wait. Okay, so why are they blocking? The answer is very straightforward. It's just that blocking operations are much easier to program with than non-blocking operations. But non-blocking operations are frequently still available. The system still frequently makes them available if you would like to use them. So this is the way that we typically use asynchronous operations. You initiate a long-running operation, and then the system says, okay, but then you get to keep running. You don't actually wait until it's finished. And so you come back to the system periodically to say, is it done yet? Are we there yet? Are we there yet? And if you're not, you go do other things. And so when the operation finally completes, you say, are we there yet? And the operating system says, yes, you are. Here's your result. And so you can go on to do the next thing with that particular resource or piece of information that you waited for. Has anybody here written programs with non-blocking operations? Okay, you haven't lived until you've gotten to do that. So maybe set that as a personal goal. I guess you'll get a little bit of experience with that in the operating system, like in the file system lab and so forth. But well, I'll talk a little bit more about that when we get to a few other things. Okay, so most systems have non-blocking APIs as well as blocking APIs. The most common one is networking. And we'll talk about how to exploit that quite a bit today. But you can also do asynchronous disk I/O. That sounds fantastic. Okay, but you could certainly do that as well. So you have various things that you can do asynchronously as well as synchronously. Another one, another really good example is WaitPid. You can configure WaitPid to be asynchronous instead of just blocking until some child process carts it, Okay, so here's some simple examples. Who here has used select? Anybody here use select or poll? What for? You're writing a server. Yeah, that's a very common reason to use select or poll. There's another one called epoll, which is even better on Linux. So like I say, you have a number of file descriptors, and you have a file descriptor set, read FDs, write FDs, accept FDs, and some timeout value if you'd like. And then you have poll, which same thing. You have a collection of file descriptors you can pass it, and timeout if you would like to come back before anything interesting happens. Epoll is similar. So these basically allow you to monitor a collection of file descriptors until something interesting happens or your timeout elapses. And like I say, it returns if a file descriptor can be read without blocking or written without blocking, or if an error occurs and you want to handle the error. Like if you are reading from a network file descriptor, a socket, and the other side closes the socket and you hit end of file. Well, that would be a good reason for select or poll to return. Okay, so you have these various situations that will cause this to return. And applications will use these when they want to take on the burden of implementing concurrency themselves, because they want to get the OS out of the way. We'll talk about some of the benefits and drawbacks. Simplicity isn't always fast, and that's kind of what you notice. You can either be fast and complicated or simple and slow, but easy to get correct. So those are kind of your general trade-offs. And the little parenthesized comment is kind of a huge understatement. So OSs heavily optimize these functions to be fast and scalable. epoll can monitor a collection of sockets in constant time. So it actually is independent of the size of the collection of sockets. How does it do that? Well, it gets a lot of help from the network card. And so you can epoll on 100 sockets or on 30,000 sockets, and either one of those operations, it's constant time. Okay? It's not going to scale with the number of sockets. It actually scales with the, well, it's just constant time. It's the operating system makes sure it's constant time. Okay, so very, very fast. Okay, so yeah, we'll talk about that in a second. So here's our example. We're going to talk about implementing a web server because this tends to be where you see these kinds of things. You can do this in a client-oriented mechanism as well. I've had the great delight to be able to do something like that, which I'll hopefully describe in a little bit. But you have a basic sequence of operations for a web server handling a connection from a client. Okay, so I'm waiting. Connection comes in. I receive the request over the socket. What do you want? Oh, you want this file? Fine, I'll serve that file for you. You access the file specified in the request, you pull it into memory, and then you shoot it out the door to the client. Maybe you close the connection after that. Maybe you keep it open so that you can accept other requests from the same client. That's very common nowadays. And we'd like to handle requests as quickly as possible. If we can exploit concurrency, then we'd like to. Because remember, this is I/O blocking, so it's going to be really slow a lot of the time. I'm going to be waiting a lot of the time. Okay, so we have several approaches we could choose from. I have the dumb one, which is single-threaded process with blocking network I/O. You can imagine how popular that server will be. Then I have a single-threaded process with non-blocking I/O, or asynchronous I/O, and then I have a multi-threaded process with blocking I/O. So these are my three options. The single-threaded version, basically think of it as, okay, I get a connection, I listen to what they have to say, I do what they want, I close the connection, then I go and get the next connection. Listen to what they have to say, do what they want, and then respond to that. So you can see that there's basically zero concurrency here. Each request response cycle is executing in sequence. Well, that's not going to be very fun. Nobody's going to want to use that server. But it is very easy to program because I have blocking operations. I don't have to think. I can just do a simple loop. You know, accept a connection. What do you have to say? Go get the file. Give back a response. That's really simple to write. I could even do that. Okay? If I have non-blocking I/O and still a single thread, now I can start implementing concurrency so that I actually have multiple overlapping requests because it'll take a little time for the request to show up and so-and-so's request may be in the network cards buffer, so I can go ahead and read that out. And I can start sending this file out, but I can't send it all out because the network is slow, and so I can send a little bit of this other file, blah, blah, blah. So you can see that you can start having concurrency with non-blocking I/O, but I still have only a single thread. Okay, so I can start getting concurrency. And what happens is each request response takes the same amount of time, more or less, but the overall throughput will be higher because I'll be able to overlap the flow for each client. So now I'm getting concurrency. I don't even need parallelism yet. I can just have concurrency here, and I get a big benefit because these operations are mostly blocked on I/O, not on the CPU. And from that perspective, you can see, well, the first version, where it's single-threaded process with blocking network I/O, that program is almost never going to be on the CPU. So the OS is going to love it. It's mostly going to be sitting in blocked queues waiting for some device. Our non-blocking version is going to try to maximize its CPU time by doing as much as it can on each I/O operation, and if it can't, it'll just put it aside and come back to it later. So you can see that the second version is going to be more CPU bound rather than I/O bound. Everybody got the concept? Okay, because I'm going to drill into this a little bit because if you haven't written programs like this before, it is a completely different way of thinking about network programming and so forth. So you have many sockets open to many clients. You remember you have some collection of file descriptors for all those sockets. Probably not in an FD set, but you would put them in there so that you could use select or pull, something like that. And for each connection, now you need to keep track of where you are in that interaction. So you start having state associated with each connection. Okay, so you can imagine you pack this into a struct, pack it into a class, choose your poison, what kind of programming language do you like? And you have to keep track of what stage am I at in this interaction. If I'm implementing a different protocol, then I'll need some other thing indicating what stage of the interaction am I in. Okay? That would be just some kind of state value, like an enum or something like that. And then if I'm receiving a request, well, I need somewhere to store it, and so you'll have a buffer, and where I am in the buffer. Have I finished receiving the entire request? You have these kinds of details. So when more data comes in, you can put it in the incoming data buffer at the appropriate location. Okay. If I'm sending the response, same thing. I need the buffer of data that I'm sending out, or I need to know where I am in the file so that I can pull the next chunk of it. And the next time I can send information without blocking, then I'll go ahead and pick up where I left off last time. Okay. So you can see that you have a lot of detail to maintain per connection. And you'll have some giant hash map, or maybe you'll have some giant array, depending on how you construct your program. But each connection has details associated with it so that you can go back and pick up where you left off. This is much simpler in a single-threaded program with blocking operations. The reason why we have all this additional complexity is because we have non-blocking operations. Okay, so the main loop. Wait for some sockets to be active. So the main loop does something really fascinating, which is it waits on all the connections at the same time. And what will happen is some subset of them will become active, which means I can read from it without blocking, I can write to it without blocking, or it has an error state and I can close it or handle the error without blocking. The rest are uninteresting. Okay? So I wait for some subset of the sockets to become active. And then for each active socket, I go through, look up that socket's corresponding state. What am I doing next with that socket? And then I do as much as I can without blocking. And then I go on to the next socket, do the same thing, and go on to the next socket, and do the same thing. Once I've done everybody's work that I can do, then I go back to waiting on everybody again. And what happens is you find that almost every time you finish that loop and go back to wait again, more sockets are ready. So you basically are sitting in that loop handling the subset of sockets that can do things. As you scale up the number of connections that you're handling at the same time, you're spending less and less time blocked on I/O because somebody's ready to do something and you can go back and handle it. Okay? And like I say, the server implements a finite state machine. It ends up looking kind of like this. Obviously, it varies depending on the protocol and the specific thing that you're doing. If you're in the phase where you're receiving the request, you pull the data into the input buffer. If you received it all, then you make a state transition to the next state. Okay? If you're in the send response state, well, push out more data until you've pushed it all out, and then maybe you enter the close the connection state, and so forth. So you have these various details that you have to do to handle each connection. You can see that it's kind of a very different way of implementing things than a single sequential, a single sequence of steps. Each blocking operation completes, and then you just go on to the next one. This is much different from that. And if you look at it, the reality is now you are implementing concurrency because you don't want the OS taking care of concurrency for you. Okay? And I say it's complicated, and it is prone to bugs. People still like doing this because it is so much faster. You can make a much faster system doing this than relying on the operating system. But you can see the level of difficulty is quite increased. Are there any questions? Okay. Now, if we have multi-threaded processes, I just got done telling you how it's complicated, but it's faster, blah, blah, blah. Well, if I want to have a simple server, then I can use a multi-threaded process and then have each thread behave exactly the same way as our single-threaded process did. And the OS gets to think about concurrency. I don't have to anymore. The OS gets to think about scheduling or who has to go next. I don't have to. The OS thinks about making sure that the appropriate thread gets waken up and so forth. So the application really only has to worry about the coordination between threads that have shared state. So a multi-threaded web server with blocking network I/O. Hey, guess what? I get to do this exactly the same way as my single-threaded server. with blocking network I/O. Receive the request, access the file, send it out the door. Okay. So you can see that multi-threading gives you a fantastic abstraction for achieving concurrency or even parallelism without having to implement it yourself. This is really nice, and so this is why a lot of people like to use multi-threading. Okay, and yeah, if I have a really slow network, then I can start a bunch of threads, and it will probably be fast, even if I'm well exceeding the number of CPUs, because they're going to be blocked on I/O, not on the CPU. Okay, does that make sense? Okay, so again, when you're evaluating situations where you have these kinds of choices to make, you think about what's most important. Is it most important to get a server implemented with basic concurrency? Well, then you choose the simple way. And if you have to achieve really high performance goals and you can't just throw money at it and buy more computers, then you pick the really fast asynchronous way that's a lot harder to program. And that's what's kind of interesting about this, because I mentioned non-blocking I/O. It is often the fastest way of implementing this stuff. I threw a lot of text up there. So yeah, you basically eliminate a lot of context switching from the the user application into the server. Into the kernel. Because remember, now I have one call to wait for a bunch of connections, not a bunch of threads each doing one call per one connection. So this scales much better with the number of connections. You have reduced space requirements because yes, you have to maintain the state for each thread, not each thread, each connection, but that means you don't have to have a thread stack, you don't have to have thread context, CPU context per thread or anything like that. So you can actually make this scale really well to very large number of connections. Guys who have used select or pull or things like that, how many concurrent connections did your system support? Did you ever try to max it out? Oh, see, now you're killing me. No? Aw. Okay, so here's the thing. I had to write a program. Let me throw this up here first. Nginx is a really great example of a server that does this. Why did Nginx get created? Well, somebody decided that they were bored, and they thought, I'm going to try to create a server that can handle 10,000 or more concurrent connections. Because up to that point, you might be lucky to have 300 or 400 concurrent connections. And people were like, wow, that's really cool. And so C10K was the way that it was abbreviated. And so they basically tried to come up with a way to scale much better to a really large number of concurrent connections. And it really scales. Like seriously, it's really good. And so it's used by a lot of companies that want to be able to support a lot of concurrent connections at the same time from very large user bases. So the list of companies using it, which is much larger than just this, it is not surprising. Okay? I had a similar experience where I was writing a server. There was a phase where I was really interested in anonymizing proxies, which can be really slow, and so you have a lot of I/O blocking there if you're testing anonymizing proxies. And again, the current, the then current software for doing it would basically run a thread per connection. And maybe you'd be lucky to have 50 connections running at the same time on a client trying to connect to all these really slow anonymizing proxy servers. I wrote a version using asynchronous I/O, and I was regularly running against 30,000 to 50,000 servers all at the same time. Really fast. Okay? So asynchronous I/O is really cool, and I will not retract the statement that you really have not lived until you've gotten a program this way. So hopefully you'll get some opportunity to do it. But like I said, it's harder to get right, so make sure you have the simple version first to fall back on if it's really critical. Otherwise, if it's not so critical, then you can take the time to engineer it correctly, and you can have an unbelievably fast system that scales really, really well. Okay, any questions about this? All right. If you're wondering why I was curious about anonymizing proxies, it was because I was doing some work for a security company, and that was an aspect of their business. So it was really fun to explore. Okay, so let's start talking about implementing threads now, because we have this challenge of how to implement this new facility for our operating system. We need to think about how it works, and we all know from CS124 that it is possible to implement threading entirely in user space. We all love it, right? Yay! Threading in user space. What could go wrong? So you can do it entirely in user mode, but it is challenging for a number of reasons. You can see that our kernel provides processes, and that's all it provides. But our process implements some mechanism by which it can actually have multiple concurrent threads of execution. Okay, so this is nice if we have a system that doesn't actually have multi-threaded processes. So if we have an operating system that doesn't support multi-threaded processes, we can implement it ourselves. Okay, so that's a good thing. It's really uncommon now to have these situations, but if you do, then you can do it. They tend to provide cooperative multi-threading. Remember cooperative multitasking? We have to relinquish the CPU. The reason why this tends to be the case is because when we are in user mode programs, we can't really generate interrupts as frequently as we would like to do preemption. Maybe you're lucky to get every 10 milliseconds. That's like often the fastest you can get the timer to go in user mode. So maybe you're stuck with 50 milliseconds or something like that to keep from putting too much overhead on the system due to generating these timer interrupts and so forth. Okay, so that's not good. And so typically doing preemptive multi-threading on these systems is prohibitive. So it has to be cooperative to make it good. Why would we want user threads in the first place, besides maybe our operating system doesn't support it? Well, even if it does support threading at the kernel level, if you think about it, if I'm staying in user mode, I don't have to actually trap into the kernel. And trapping into the kernel is not the fastest thing we can do. Okay? So if I can stay entirely in user space to create new threads, to destroy threads, to context switch between threads, I don't get the kernel involved at all. The kernel doesn't get any sort of idea like, ooh, you know what, I'll context switch away from you. Well, if you stay in user mode for all of that, then your threading is a lot faster. You're not incurring all that overhead. The issue is, why do we like threads? Well, I like threads because they're a good abstraction if I do blocking operations. And threads are great when I want to run on multiple CPUs. If I do user space threading, I can't solve either one of those problems effectively. This is the issue with user space threading. So I want to use threads to achieve concurrency in programs with blocking system calls. What do I do if I want to do a blocking system call? Okay, so thread N traps into the kernel and says, I want to do something that's long running, and the kernel's like, great, I'll set that up for you, and guess what? You don't get to run anymore. So one thread deciding to perform a blocking system call blocks all the other user space threads. Okay, that's an issue. Also, we frequently would like to take advantage of multiple CPUs. Well, if the kernel doesn't know that you have multiple threads in your application, it can't put you on multiple CPUs. So why would you want to use user threads in the first place? Well, that's a really good question. If you have a lot of threads that are communicating a lot and collaborating a lot, synchronizing with each other a lot, then it might make sense to keep it in user space. But if you have blocking system calls or you have a desire to run on multiple CPUs, it kind of kills user space threading. Okay? So another option, obviously, is to provide some level of kernel threading support, which is thankfully what most operating systems do now. So the kernel can actually be intelligent about doing this stuff. With blocking system calls, no big deal. The kernel will say, hey, you know what? I've got 4 other threads in that same process. This thread just became blocked, but I'd like to give this process more of its time slice, so I'm going to switch to another thread in the same process, and then I don't have to change the MMU configuration. So I save me some time too. Okay, so that's nice. That's one benefit of kernel threading. Parallelism, same thing. This thread will be scheduled on this processor. This other thread will be scheduled on this other processor. Now I have true parallelism. Okay? The drawback is what the benefit was before with user space threading. Now I have to trap into the kernel. And that's slower than just sticking around in user space to do this stuff. Okay, so you can see that there's benefits and drawbacks of either approach. You can imagine that most people do kernel threading because the benefits outweigh the drawbacks. What can you do? Okay, any questions about these two? All right, so since the operating system is what provides multitasking support, there has to be some kind of kernel level schedulable thingy. We call it a kernel thread, which is really confusing because we just talked about kernel threading. Sorry, that's just the terminology. There's a number of places where the terminology is reused. So each thread of a user application must correspond to some schedulable kernel level task, and we call that a kernel thread. So that maintains CPU registers, program counter, stack, all of this kind of stuff. This kernel thread thing is not a process. This will become really obvious when you get into the user mode program support in Pintos. You have a kernel thread, it executes a process. So the two things are paired, but they're not the same thing. The kernel thread is basically the process's representative inside the kernel. So the kernel thread is very lightweight. And kernel threads can become blocked, they can be resumed, and so forth. So we'll talk about the relationship with these, between these things much more next time. But we're just sort of introducing some of these concepts. So we have a kernel thread that is in the kernel. It's a kernel level schedulable task. And then we have threads in the process. So the question is, how do we map threads in the process to kernel threads? And that gives rise to a number of threading models that have been attempted or utilized in various operating systems. So like I said, different threading models have different ways of mapping these user threads to kernel threads. One is called many-to-one, where I have all the user threads in my process mapped to a single kernel thread. Hopefully that's ringing a bell for you. Hey, that's exactly like user space threading, because I have all the threads in the user side of the line, and they all map to a single kernel thread. So the kernel thread represents the process, not the threads, in the user space application. Okay. Like you say here, one user thread decides to perform a blocking operation. Well, too bad. The kernel thread becomes blocked, so all the other user threads are not allowed to proceed anymore. The kernel switches to another kernel thread and allows that process to execute. Okay. Are you guys getting it, I hope? Okay. There actually is a threading library that does this. It's called GNU Portable Threads. And you can see portables right in the name. So this is for situations where you don't have kernel level multi-threading support and you'd still like to be able to write multi-threaded programs. I hope you never find yourself in that world. Threading is not that hard to implement. So if you already are implementing processes, implement threads too. Another approach is one-to-one. So now every user thread in a process is mapped to its own kernel thread. This is identical to the kernel threading approach that we talked about already. Okay, so now I have kernel-supported threading. Each user thread in a process mapped to its own kernel thread, so if one user thread decides to perform a blocking operation, it traps into the kernel, the corresponding kernel thread becomes blocked. The kernel can now switch to another kernel thread for the same process. So another user thread is able to progress while that one user thread is blocked. Again, I hope you guys are seeing. You have user thread, which is like the tip of the iceberg, and then you have the kernel thread, which is the other tip of the iceberg. That was a bad analogy. Anyway, and this is the model that most operating systems actually provide. Like I say, it tends to be the most straightforward to implement to actually provide all of the facilities that we'd like to have. Okay, so those are two. You can probably guess that there's another one somewhere in the middle, right? If I have many-to-one and I have one-to-one, well, you can also have sort of a many-to-many threading model, aka a hybrid threading model. And you have some number of user threads mapped to some other number of kernel threads, usually fewer. The idea is that you have benefits from both approaches. User mode threading is really nice because spinning up threads is fast, destroying threads is fast, synchronization between user space threads is really fast. But every once in a while, user threads want to perform blocking operations. So that's where kernel threading is really nice because I can just switch to another user thread. Okay, so if I have these things, so n user threads and m kernel threads, I'd like to somehow map our user threads to our kernel threads in a way that maximizes the system performance so that I can get the benefits and I can have my cake and eat it too, so to speak. So I have a lot of competing, cooperating user threads, then I can map them all to a single kernel thread, and then those threads never need to trap into the kernel because they just keep interacting with each other. Go us. So we reduce system calls and kernel level context switches. And if user threads become blocked on I/O frequently, well then I'll just give it a kernel thread to use all the time. And then that won't hold up other user threads in the same application. Does this make sense? Seems really cool, right? Turns out this is really hard to implement. The reason why is because you have scheduling, thread scheduling, distributed on both sides of this kernel user space line. Becomes a very important line. So like I say, most operating systems just use one-to-one because it's so complicated to get right. Windows 7, you know, for all my whinging about Windows from time to time, it has been really innovative in trying to introduce a hybrid threading model so that they can actually leverage both benefits of both approaches. Okay, so you have threads in the process. Those are user space threads. We have kernel threading support, so we have a couple of kernel threads. And you can see that we have a thread scheduler in user space and we have a thread scheduler in the kernel. Okay, so they're both making decisions. How do they coordinate? Okay, if we don't have any way of coordinating, then we can't really do this clever thing of mapping user space threads to kernel threads in an intelligent way. I need to know when threads do blocking calls, and I need to know when threads are just cooperating with each other and being really happy together. Okay, so let me see. I'm going to try to spin through some of this because we're almost out of time, or actually we're over time. So yeah, if user thread layer can intercept blocking system calls, then it can actually do some of these things itself. So if I can get a hand in between the kernel and the program, then I can actually handle some of these situations. But if not, then I'm stuck. Okay, also, you'd like to know if the user thread layer can know what the kernel's seeing as far as program behavior. Are things being preempted? Are they being blocked on I/O frequently? So if the user thread scheduler could see what the kernel's seeing, then we could manage this a little bit better. Okay, so let me throw this up there. One of the most common approaches is actually called scheduler activations because what we do is register a callback with the kernel so that when various things happen with kernel threads, we can be informed about it in user space. So this kernel thread was just preempted. Okay, that corresponded to this user thread. Maybe it's really nice and I can map it to some other, I can share one kernel thread with a bunch of user threads. A kernel thread is about to block or it's about to become unblocked and so forth. So now you can start getting a peek into what is happening. We call this mechanism an upcall from the kernel into user space to inform the user program that something is happening that it should care about. Okay, and it calls this thing called an upcall handler, which actually cares. Okay, so yeah, you can read about this. I don't want to take too much time for this. This mechanism of upcalling, again, you're trapping. You're not really trapping in this direction. You're just calling into user space. So you have to change stacks. You have to go through a gate. So it's not literally a trap. It's something similar. It's akin to a trap. But it takes time. And we're also invoking, hopefully fast code, but we're still invoking more code for scheduling. So you can see that it does affect system performance. Okay, and so you don't see a lot of benefits. You don't see a lot of people picking this up. Of all of the hybrid threading model implementations, about 2/3 of them use scheduler activations. Not a lot of attempts have been made because it's challenging, but of those, most of them use scheduler activations. If you're curious, you can look at the Marcel library, which attempts to use this approach. And that's all I want to say about that. Next time, we'll go ahead and start diving into more low-level details of how kernel threads work. So I'll see you all next week.